Hello everybody. Let's continue with our lecture series on this optimal control guidance and estimation. We have just started some estimation concepts last time. We actually studied this LQ observer followed by some overview of Kalman filter implementation and things like that. So, next couple of lectures we will go through this derivation process of Kalman filter to understand it much better, and then talk about some issues of implementation and things like that actually. Alright, so this is in this particular lecture we will primarily concentrate on a review of probability theory and random variables, which is actually needed for derivation of Kalman filter later. Alright, these are some of the very basic definitions of probability. There are two different ways of looking at it actually. Okay. So, first definition is something like this: if there are n exhaustive equally likely elementary events in a trial and m of them are favorable to an event A, okay, then probability of A is defined as m over n actually. Alright, so you have n exhaustive elementary events and m of them are favorable to event A. That's how it goes. Then probability of A is nothing but m by n, which means possible outcomes favoring event A divided by total number of possible outcomes. It is very intuitive actually. Okay. So, definition 2 tells something very similar, but in a little bit different way. What else is, if a trial is conducted n times and m of them are favorable to an event A, then there is something called relative frequency RA, which is defined as m over n. It does not define probability directly. It tells because sample space is in not large and all that actually. So, that relative frequency turns out to be m by n, and in the limit where n tends to infinity, okay, and if the limit exists, okay, then the limit is defined as probability actually. Okay. So, essentially it tells you that the number of samples should be large. Then only you can define something like probability basically. What are sample space and events and things like that? If you think about sample space, this is defined as something like the set of all possible outcomes in a trial is called the sample space S for the trial. Okay. And the elements are also called sample points actually. So, examples of tossing a coin is something like this. You have this something like, if you toss a coin one time, then this is either head or tail. So, you can think of head as a sample point and tail as a sample point, whereas the sample space contains either all heads or all tails. So, H and T, if you take that way, that is the sample space. But simultaneously, if you toss two coins, then obviously there are 4 possibilities. So, either you can get head and tail, or tail and head, or tail and tail, or something like that. So, each of these combinations are nothing but sample points, whereas the total set S is nothing but the sample space actually. Similarly, if you toss a die has 6 sides actually. So, here each of these 1, 2, 3, 4, 5, 6 are sample points, whereas the total collection of all the sample points, if you define that as a set, that is nothing but the sample space actually. So, the event is defined as something like every subset of S is something we called an event. Okay. So, if you take any subset of S, okay, either single element, 2 elements, things like that, or even the full set, is nothing but an event actually. Okay. And there are something like 2 special events. One is phi, which is called impossible event, null set actually, and then the total set, the entire everything is there in that. So, the event S is called the certain event. If you take the total thing, it is guaranteed to have everything actually. Okay. So, for example, if you take 1, 3, 5 out of this set, then this is an event, and suppose this you just collect head and tail out of that, then that is an event actually. Okay. There are other concepts, something like disjoint set, disjoint event, exhaustive event, complementary event, things like that. So, this is very similar or very close to set theory actually, if you know that way. So, 2 events A and B in a sample space S are called mutually exhaustive or disjoint events if there is nothing in common between them. That means, A intersection B is null set actually. And if the exhaustive, I mean if these two A and B are exhaustive, if the union of them turns out to be the sample space. Okay, so everything is contained in that if you take union of that. And things like complementary is something very interesting. If you have A union B is S, but A intersection B is phi. That means they complement each other very well, and together they kind of contain all sample space, and in between there is nothing common in between them actually. Okay, so that's kind of thing that you are looking for here. And there is something called complement event also. Okay, and that is defined as for any event A, there is a complement event A bar such that A union A bar is S actually, and also A intersection A bar is phi. And obviously, if you take complement of complement, that means A double bar, obviously it turns out to be A basically. And some facts are something like this. So, you have this probability of phi is obviously nothing there, so it is 0. Probability of the sample space is 1, and probability of A intersection B is defined as, it turns out to be probability of A into probability of B, and probability of A union B is summation of them, provided there is nothing common in between them. Okay. And if it turns out to be a subset of B, okay, then probability of A is going to be less than equal to probability of B actually. So, these are some of the results that sometimes come handy in probability theory basically. Remember, all of that you may not need while deriving Kalman filter, but just sort of kind of precursor knowledge will also help us understand it slightly better. There is something called conditional probability, and then conditional probability is defined something like that, like this. The probability of outcome A given an occurrence of outcome B is something called as conditional probability of A given B, and this is defined as probability of A given B is probability of A intersection B divided by probability of B basically. There are examples, and then if you are really interested, you can see couple of probability theory books, or even nice mathematics books like Radhakant and all that. So, you can get a lot of ideas and including examples and all that. And using some of these concepts, just for your information, there are nice advanced filtering theory, filtering techniques have been proposed recently. So, they are not very useless that way. In other words, even though they are not directly useful in Kalman filter per se, if you know this, then you can understand other filter techniques also better basically. Then okay, these are something like discrete events and all that. So, what you are really interested in systems theory is typically something that is associated with continuous signals. You know, these systems, I mean, when we talk about x dot equal to some f of x u and things like that, then that is typically x of t is a continuous variable and things like that. So, what if those things are randomly varying actually? So, in that sense, you can define something called random variable, okay, and random variable is essentially a function. Okay, remember this, it's actually a function that maps all points in a sample space to real numbers. Okay, but the exact value of the real number is not known actually. Okay, so for example, if you think about x of t, okay, there is a value. Okay, so if given a t, there is a value, but the exact value, the numerical value is uncertain actually. This is not known really. Okay, so that's called random variable actually. In other words, a variable whose values are random, but whose statistical distribution is known basically. Okay. Also remember that is I mean any random variable cannot be purely random in that sense. We have to really talk about some sort of a statistical distribution associated with that. We'll talk about that in a while. So, that is called probability density function and things like that. So, those things are known, but the value, exact value that comes out in each experiment is typically unknown actually. So, in case of continuous random variables, the probability of any discrete event turns out to be 0 obviously, because it is very intuitive to see that, it is not difficult at all. Suppose you have got a continuous number sense actually, let us say you are talking about this between a number between these two. So, obviously, if you talk about real numbers, there are infinite numbers in between. So, if you talk just one point out there, then obviously, the probability turns out to be 1 over infinity. So, that is not defined. So, that is 0 because 1 over infinity turns out to be 0 actually. Okay. So, how to go ahead about that? So, we can talk about a probability of a single discrete event here. So, then it turns out that we have to evaluate the probability of events within a finite time interval. Let us say we talk about this interval now. Okay. Now, theoretically speaking, this I mean there are infinity numbers in between these two, okay, all right, and there are infinity numbers between the total interval also basically. So, it turns out to be now there is some infinity over this interval and infinity over that interval. Okay. So, if you denote it as something like let us say you denote it as something like a b and then it is small a small b. So, what you do is this is like probability turns out to be length of a b divided by length of a b probably. Okay. Then this is something like infinity over infinity and obviously there is a finite number associated with that after that actually. You can, if you given a particular function like that, you can use L'Hospital rule and then get number for that actually. But intuitively it is obvious, if you take some finite time interval, then you can define a finite number associated with that and that turns out to be the probability of that actually. Okay. But how do you define all these this distribution function and things like that? So, there are concepts like cumulative distribution function. Okay. The cumulative distribution function is defined as something like this. Okay, f capital X within bracket small x. Okay, that is defined as probability between the interval minus infinity to x. So, it defines it represents a cumulative probability of the continuous random signal x actually for all events up to and including x obviously, right. This is suppose we start from minus infinity, okay, and come all the way up to x, okay. Then whatever interval you are talking here that will define what you want actually. As represents a cumulative probability of continuous random variable x for all events up to and including x basically up to this. So, properties of this capital Fx of x, it turns out to be 0 as x goes to minus infinity. Okay, when x starts moving towards minus infinity, obviously it goes the width becomes narrower and narrower. Ultimately, it turns out to be this cumulative distribution function turns out to be 0. What about x goes to plus infinity? Then it contains everything, and hence f of x goes to 1. Okay. So, how does it vary actually? If you see that, okay, if you want to see that how does it vary actually, then it turns out that, okay, if I plot something like minus infinity to plus infinity somewhere and I talk about some PDF value as something like 1, then it starts from infinity and then I start from 0 and then go towards that actually. Okay. So, obviously f of x is a non-decreasing function of x. It keeps on continuously increasing. Starts with 0, slowly starts building up, keeps on increasing and somewhere it stabilizes at 1 actually. Okay, so that's the concept of distribution function, cumulative distribution function. Now, if you see an interesting property of this distribution function, okay, the derivative turns out to be 0 here and turns out to be 0 here. Okay. So, obviously, derivative starts increasing and then decreasing and then it becomes again 0 and all the time it kind of remains positive. So, see the slope actually. Okay. Slope is all the time is positive. Initially it is 0, finally it is 0. It's somewhere in between it is maximum actually. So, derivative contains a lot of information and that is how this derivative is defined as probability density function. And this is what is this is what you will come across in lot of probability, lot of this random variable concepts and all that actually. So, the probability density function now is defined as derivative of probability distribution function actually, cumulative distribution function. Alright, so this now this is defined as small f. So, small f x of small x is d by dx of f x actually. So, what are the properties now? Obviously, integration of f x from minus infinity to plus infinity is 1, okay, and obviously as I told here, it's always a non-negative function actually. Okay. Now, what is the beauty of defining this? Okay, it turns out that we can evaluate probability between some segment a b once we know this actually. How to do that? So, this is p x of a b is nothing but f x of b minus f x of a. So, it is minus infinity to b obviously by definition, and this f x is nothing but integral of this okay, p x of a b is f x b minus f x a, which is nothing but integral of minus infinity to b, this one, and integral of this one actually. Okay. So, this turns out to be because this f of x, capital F of x is integral of this small f of x, okay, if you take the reverse thing actually. So, then if you combine that, okay, if you work on that actually, what happens is minus infinity to b and change the interval, change the limits, okay. So, it talks about a to minus infinity, then it becomes positive actually, okay. So, now what you can see is, okay, I can think about now minus infinity plus this minus infinity goes, so I can combine these two and it turns out to be integral a to b, okay. And dy dx of f of x is nothing but f x actually, okay. So, while I can put it that way, okay. So, what sometimes people tell, okay, I do not have to do all that, I just take this as a definition actually. So, p x of p x in the interval a b is integral of f x x dx actually. So, once you know this small f of x, it is lot of information, because you can simply evaluate probability directly and many other things also possible actually. Now, something mean and expected value, and especially if it is a discrete event, okay, it is rather easy to see. You can tell, okay, mean is nothing but if I take n trials, okay, and the possible outcomes are something like x 1, x 2 up to x n, and each of that has probabilities p 1, p 2, p n. Then what happens is the number of occurrence of outcome x 1 is nothing but x I in general is nothing but p I out of here into n, okay. So, this x I is, okay, I can compute this way, okay. So, the mean turns out to be something like this, okay, this p 1 of p 1 n into probability of that which is x 1 itself, and then it is p 1 of p 2 into n into x 2, okay, and all the way up to that, okay, up to n, and then divided by the total number of things actually, okay, and n is the possible outcomes. So, divide by total thing actually, okay. So, then it turns out that, okay, if n cancels out everywhere, okay, then it turns out that, okay, it is nothing but the summation of p I x I basically, okay. So, this is rather easy to see, but then what about continuous variables and all, okay. So, continuous variable is defined this way. We talk about expected value now here. So, expected value of x is integral of minus infinity to plus infinity x f x dx sort of thing, okay. And what happens is for functions of random variables now, suppose you have a random variable, but what about some sort of a function of random variable actually. Now, if you take a random variable x which is in discrete domain, okay, it can take only discrete numbers and all that. So, then you talk about a function of that, then you talk about expected value of that, okay. Then turns out to be like this, okay, summation from I to I equal 1 to n p I g of x I. But if it is a continuous case, that means x is a continuous random variable, then expected value is defined something like this actually, okay. And the great property of this expected value, okay, is it turns out that the expected value is a linear operator, okay. So, once something is a linear operator, it's very handy, you can do many operations rather very easily actually. We will see that some of these things, I mean this particular expected value and all will be heavily used in Kalman filtering also. And there we will use this linear operator behavior very frequently actually. Okay. So, what do you mean by an operator being linear? It satisfies the principle of superposition. That means, if you take two signals x1 plus x2 and take expected value of that, then it is nothing but the expected value of x1 plus expected value of x2. Similarly, if you multiply this random variable with some constant c, then expected value of that turns out to be c times expected value of the value itself, random variable itself. So, these two will be very useful later. Then it is something called statistical moment. Okay. And because this g is in general can be any function. So, we are not interested in any function per se, but this is the typical function with x to the power k basically. Okay. So, when you take g of x is x to the power k, what happens there in that particular case? Okay. Obviously, expected value of x to the power k by definition is g of x multiplied by PDF of that actually. So, g of x multiplied by this fx of x, whatever you see here. And for example, if you talk about expected value of x square, then all that you have to do is integral of minus infinity plus infinity, then k is 2 here. So, x square, that is what you put here, and then evaluate this integral. And this is typically called a second moment of the random variable. Okay. If you put x actually not x square, then it is called first moment actually. Okay. So, in general it is kth statistical moment of the continuous random variable x, that is how it is defined actually. Now, why it is useful this second moment and things like that, because this variation concepts actually. Okay. So, anytime you talk about a signal that is randomly varying, there are two things that is very critical. One is what is the mean value about which the variation or deviation happens actually. And then after the mean value, what is the spread of the variable spread of the values actually. Okay. Now, that spread of the values is given by the second moment, and that is typically called variation, and square root of that will turn out to be standard deviation actually. Okay. So, what is variance? Variance is what is the random signal minus the expected value, that means mean value sort of thing. So, you have some randomly variable, some randomly varying signal, okay, or random variable x. All that you are telling is seeing the difference between the value from its mean value basically, and then taking that as a function there, g of x. Okay. So, then if you do that, then you operate in the second moment and things like that actually. Okay. Then you operate get this sigma x square. In other words, sigma x square is nothing but this particular deviation value, what you get there whole square actually. Now, essentially this is a number finally, the value is not known, but it is a number, okay, and this is also a number. It is a expected value is a deterministic mean value sort of thing, it is a number. So, when you have this this sort of operation going on a square, you can actually use this a minus b whole square formula. Then it turns out to be something like x square minus 2x expected value of x plus e to the power expected value of x whole square basically. Okay. But remember, expected value of x is nothing but mu of x, that is by definition actually. Okay. So, what happens this is nothing but mu x square by definition, this is mu x and that is mu x square. But expected value of x square we do not know, I mean we have to just keep it actually. Okay. So, but remember now it is we will use this linear property of the expected value operator. So, expected operator is a linear operator. So, then what happens, we can expand this bracket and then tell this is nothing but expected value of x square minus all the way the expected value can go, I mean this is nothing but mu x, mu x is a number, remember that. So, 2 mu x will come out, then expected value of x will come here, okay. Then it is nothing but mu x square. Okay. But what is expected value of x? Again it is nothing but mu x. So, this turns out to be 2 mu x square and this is plus mu x square. So, it ultimately turns out to be minus mu x square. So, sigma x square in general is expected value of x square minus mu x whole square actually, minus mu x square. Okay. So, this is a nice property because you do not have to do this all the time, you can just see expected value x square minus mu x square actually. Alright, then by definition the standard deviation is nothing but variance of x, sorry, square root of the variance of x. So, sigma x is nothing but square root of sigma x square, that is what the definition tells actually here. Okay. And typically it is a positive square root actually. Okay. So, the point here is this mean and variance, okay, or rather standard deviation and all that are very useful statistical properties of any random signal. So, somebody tells it is a random signal, you cannot tell where the number will lie, but if he carries lot of experiment, we will be typically knowing what is the average value and what is the standard deviation or variance actually. Okay, and in fact, the entire Kalman filter turns out to be I mean kind of making kind of a track record between this mean expected value and variance actually, or rather covariance what we will call there actually. Okay, because it turns out to be a vector signal, then you see what you are talking here is scalar variables and all, but when it turns out to be a vector of random variables actually, then you talk about something called covariance. Okay. And then the entire filtering theory is expected value and covariance matrix. That's what it will talk about actually. We will see that as we go along. Okay. Then this particular distribution is of very importance in any probability theory, including Kalman filtering. And the reasons for this popularity of Gaussian distribution is three things. First thing is it is close to the nature. Okay, that means by default many of the distribution turns out to be Gaussian actually. But on top of that there is a central limit theorem as well, which tells us that sum of random variables with any distribution, you can start with any distribution, but if you keep on adding them up, okay, so sum of random variables with any distribution ultimately tends towards normal distribution. Okay, so that is why this normal distribution or Gaussian distribution is very popular actually. Yeah. But that is not the only, that is not the thing. What is also good about it is mathematically tractable and attractive actually. That means you can do lot of algebra very easily actually. And what is the probability density function associated with that? This is something like this. Okay. It is characterized by mu and sigma square. Okay. And this probability density function, okay, turns out to be like something like this. 1 over square root of 2 pi sigma square exponential minus half this thing actually, where x varies from minus infinity to plus infinity. You take any value of x, the density function will give you a number actually. How does it look like? Well, if you plot it something like this, okay, if sigma is small, it will turn out to be something like this, okay, and if sigma is large, then it is a large distribution. I mean, it turn out to be like this actually. Okay. So, what happens here is it depends on see mu remains same probably both the plots, but if sigma is small, most of the values are centered around mu basically. So, but if sigma is large, then many of the numbers are deviated away from mu basically, that is what it tells you. Okay. But area under the curve probably will remain same, because ultimately if you take minus infinity to plus infinity integration, okay, both of that will give us 1 actually. Okay. Alright, so if you take a cumulative density function, okay, this one what we discussed here, sorry, cumulative distribution function, okay. Okay, cumulative distribution function is something like this. So, ultimately probability between this interval A and B will turn out to be like this. And this is very interesting property of that, most of the time it is useful from 2 sigma onwards especially. And if you take something like okay, minus sigma to plus sigma, in other words, you have got a sigma value here. Okay, typically by this actually it turns out to be something like 3 sigma value. Okay. So, this one is 2 sigma, this one is sigma, and similarly this is sigma, this is 2 sigma, let us say. Okay. So, if I take this one, okay, and then talk about probability between this interval, okay, that is minus sigma and Well, mu minus sigma to be exact, and this is mu plus sigma basically. Okay, if I take the probability between this interval, it turns out to be 68%. That means if I take the area under this, okay, and divide it by the total area, it turns out to be 68%. Okay, and then if I talk 2 sigma, that means between this interval now, okay, it is much better. It is 95%, 95.5% already. If I take 3 sigma, it is 99.73, okay, and for all practical purpose, we typically stop at 3 sigma value, okay, plus or minus 3 sigma value. But what is good? Remember, if you suppose you are estimating something, okay, you do not know actually what is the value, but you are estimating something. You got this value mu, okay, and you tell, okay, all my signals are bounded very close to the mu. That means this is how it is, okay. Sorry, ideally, okay, this should not be like that. Okay. It tells, okay, my sigma is small actually, okay, so that is typically very close to that. So most of the values will fall close to sigma, really, close to mu, okay. Then it's a good estimator actually, okay. And I have a lot of confidence in something with where sigma is small. So if any sensor that you are using and then doing some experiment to characterize whether the sensor is good or bad, you should not only see the mu's, you should also see what's the value of sigma associated with mu. If sigma is small, then the confidence on that value, on that average value mu is much higher actually. Okay, but somebody tells us only mu and then remain silent on about sigma is not good also. Because if you carry out, let us say, I mean, just to be simple, 2 experiments, and probably one value is minus 0.01 and other value is plus 0.01, then the average value is 0. And another 2 numbers where the one is minus 1000 and other one is plus 1000, the mean is still 0. So just talk about mean value does not give us the complete picture. It always has the variation associated with the mean value that gives us the complete picture actually. Okay. Alright, so these are the Gaussian distribution, and why it is okay, mathematically tractable, let us see actually. Okay, there are properties of normal distribution, something turns out to be like that. If I construct another random variable, okay, as a linear combination of this, as a linear function of this original random variable, something like y equal to x plus b, then I can directly write the PDF of y basically. Okay. So PDF of y, which turns out that it will the average value mu turns out to be a mu plus b, okay, and the variance turns out to be sigma square, okay, sorry, a sigma sort of thing. Okay. If you compare these, okay, the variance turns out to be a sigma, well, the a square sigma square, but the sigma square is the original variance. So the variance of y turns out to be a square sigma square, and average, I mean, that mu is the original mean value for or expected value for x, and the expected value for y will be exactly same linear function of mu. That means if I know y is x plus b, I can directly write what's the, I mean, mu of y, something like this, and sigma of y will turn out to be a sigma basically. Okay, that is one thing. Other thing is, if I take, let us say, x1 and x2 are 2 independent random variables, okay, with characteristics being these things. That means x1 has mean value mu1 and then variance sigma 1 square. Similarly, x2 has mean value mu2 and variance sigma 2 square. Okay, then x1 plus x2 will satisfy this. That means its mean value will become mu1 plus mu2 and its variance will become sigma 1 square plus sigma 2 square. Okay. Alright, then the PDF becomes something like this. Fx of x1 plus x2 turns out to be something like this actually. Okay. So it's easy. I mean, if you know that it's a normal distribution, then many things can be done just by looking at some of these nice properties actually. Okay, then there is some concept called conditional probability and things like that. Okay, so you have these 2 continuous random variables x and y are statistically independent. Okay, if their joint PDF, okay, something called joint PDF now, fx of xy is equal to the product of their individual PDFs. That means, if I talk about fxy of xy, it turns out to be multiplication of both actually. And this is what I was talking a little while before. This Bayes rule or Bayesian probability and things like that. This is based on which people have proposed very neat filtering ideas actually. A very recent literature, if you see, the things are available, Bayesian based belief for filtering theory basically. Yeah. So, it talks about conditional probability. Okay. And first thing is continuous. That means, PDF of a continuous random variable x given the presence of a continuous random variable y is defined something like this, and that expression turns out to be like this. Okay. Similarly, but if it is continuous discrete, that means PDF of discrete x given the presence of continuous y, okay, turns out to be something like this, little more complex actually. Okay, here is a neat concept which we will need very quickly. Okay, this concept of something called autocorrelation. Now, remember x is a time varying function, I mean time varying random signal. So, x of t1 and x of t2 will be different actually. Okay. So, what about expected value of x of t1 into x of t2? Okay. Okay. So, if you take t1, t2 are two sample times, then you construct the x of t1 into x of t2 and then take expected value of that, what will turn out to be, and whatever it turns out, that is defined as autocorrelation actually. Okay. And the theorem tells us that if the process is stationary, okay, so that means by definition the PDF is invariant with time, PDF does not change actually. Then this autocorrelation, okay, Rx of t1 t2 is just a function between t1 minus t2. Okay. This is just a function of t1 minus t2 basically. Okay. So, Rx of t2 minus t1, okay, Rx of t1 t2 is nothing but Rx of t2 minus t1, the interval between them, okay, this tau basically. So, I can always write it as a function of tau instead of writing t1, t2 and all. So, this Rx of tau then is expected value of x of t into, remember t1 is t and t2 is t plus tau basically. So, this is how it is. Now, this is a nice property, this Rx gives us many interesting things actually. Now, let us see some things like this. Now, we have let us say two signals x1 and x2. Now, we want to see which is more correlated with respect to itself actually, autocorrelation tells us that actually. Okay. If you see x2 and x1, x1 turns out to be short, but it is wide actually. Okay. So, if I take a value t1 here, okay, let us say I put a value t1 here and something like t2 here, then there is, if I take x1, then there is something which is non-zero, okay, and here is something which is non-zero. That means, the multiplication of that will not turn out to be 0 basically. Okay. But what about x2, if I take that one? Okay, well, this is there is a value here, but there is nothing there, that is 0 basically. Okay. All right. So, that means x2 signal is less correlated to itself basically, because if I take a difference between t1 and t2 higher, okay, then it is quickly going towards 0 actually. But if it is I mean if it is wide, okay, autocorrelation function turns out to be wider, then it turns, it is something like more correlated to itself actually. Okay. So, this means, okay, this picture tells us that x2 is less correlated with itself than x1 actually. Okay. x1 is more correlated to itself, because even if the difference between t1 and t2 becomes wider and wider, the numbers do not go to 0 very quickly basically, because this will still turn out some number, positive number is non-zero basically. That is the reason. Now, what is the limit in case, if that is the case? Now, let us say this width turns out to be smaller and smaller, ultimately the width turns out to be 0, then what actually? That means, if I talk about the same time instant, okay, then I will get some value for this x of t1 into x of t1 has some value, but the moment x of t2 is slightly different from x1, okay, that means t2 is something like t1 plus delta t, where delta t is a very small value actually, then this number is not there, that means one of that is 0, okay, and hence everything turns out to be 0 actually. So, in that particular case, this something defined like this, and that is nothing but white noise. Okay. Might have heard about this white noise many times and all that actually, or maybe we will see that in our Kalman filtering derivation also basically. So, all that it tells us for a stress, first of all the signal has to be stationary, the PDF should not change, and then it tells out that okay, R of Rx of tau is nothing but just the direct delta function basically. Okay, so that means if tau is 0, there is no interval between two numbers t1 t2, then it turns out to be some finite value a, otherwise it is 0 basically. Okay. So, note that white noise is a very important building block, okay, for random signal processing and including Kalman filter. Okay. And standard way of handling colored noise is to construct the colored noise as output of another system with white noise being its input and augmenting this system with the total system. For example, if you have this let us say, let me give an example here, let us say you have this x dot equal to x plus something like w, but w is not white now, then what do you do? Okay. So, what you tell is okay, I will construct another some sort of a transfer function or some function here, whatever it is, then where I will give something like w1, I will give w actually, but this is a dynamic system, remember that. So, maybe something like a first order system or second order, it depends on all that, the noise behavior basically. But then what you will do, suppose it is a first order, then you put a w dot equation, okay, and then tell okay, it is something like well, if you see this expression, it turns out to be what actually w by output by input is a by s plus a. Okay. So, something like w dot plus a w is equal to a w1 actually. So, if you tell w dot is nothing but minus a w plus a w1. Okay. Now, w has become a state actually. If you see this thing, that is not a random noise anymore. This will become a state, but this one happens to be random signal again, but this then the modeling has to be done in such a way that w1 turns out to be white actually. Okay. So, that means again you come back to the entire, if you see the visualize the entire system, okay, w1 has become the noise actually. Okay. Now, w1 is white actually. Okay. So, this concept is called shaping filter, and typically this is not a very simple thing to get this transfer function what you are talking here. But for important phenomenons, these things are available as part of the modeling process basically. Okay, so, for example, if you talk about let us say wind gust and all that, there are Dryden models and things like that way. So, which will do this exactly like this. The Dryden model is all that it tells is if I take a white noise and put it in that, the output of that function what I am having will give me that particular noise which is physically happening basically, that is called color noise. If something is non-white, it is called color noise actually. So, input will be white, but output will be colored, and then I can augment the original system that way, where the input is still a white noise, and hence I can use Kalman filter actually. We will see an example in a subsequent class also basically that way. Now, the same thing can be interpreted in different ways also. Now, if you talk about time domain, and this Rx of tau is can be represented something like this, exactly at 0 it has some value, and that is not, and in anything like this can also have some frequency domain interpretation as long as the process is stationary. So, you construct this Fourier transform sort of thing, then this is defined something like this, and it turns out to be just a constant number, okay, irrespective of omega. I mean, if you plot it as a function of omega, it turns out to be just constant. That means, it contains all frequency spectrum actually. Okay. So, there is another interpretation in the frequency domain basically. Okay. Then there are concepts like something like cross correlation and cross covariance, things like that. Okay. So, first thing is cross correlation. Suppose here we are talking autocorrelation, we talked about the same signal, okay, x and x. But suppose the signal is different, we have something like x and y, then what actually? Okay. In that case, it is no more an autocorrelation, but it is something like cross correlation. okay, and it's very similar to that, but the fact is it is not x, y here actually. Okay. And again cross correlation function is also only a function of tau. That means it does not depend on, it is not really a function of t, but it is function of tau really, the difference between t2 and t1 sort of thing for any stationary random process. Okay. And if you have cross correlation, you also have cross covariance. Okay. So, the cross covariance is defined something like the expected value of x minus mu x and multiplied with y as a function of t plus tau minus mu y actually. Okay. Then something called stationary stochastic processes and all. So, tell okay, when is this when the stationary processes x and y are uncorrelated, or when they are correlated like that actually. So, they are uncorrelated if this cross covariance, I mean this function that we just talked about, cross correlation function, okay, turns out to be just multiplication of these expected values of the two. Okay. So, if you talk about right this stochastic process x and y, and if somebody tells, oh, these are not correlated, these are uncorrelated, then this operation, I mean this result can be used actually. And in fact, we will see in Kalman filter derivation many times we will use this actually, okay, because process noise to sensor noise is uncorrelated, and initial condition to something like sensor noise is uncorrelated, like that actually. You will see many things getting used there. So, you can define it this way, or equivalently you can define something on the in terms of cross covariance actually. Okay. Instead of cross correlation, which is expected value of these two multiplications only, you talk about the deviation of that from their own mean values, and then take multiplication of that, and that turns out to be cross covariance. So, the cross covariance matrix, okay, of that is can be written like this, and then if you see, this is nothing but this expected value of this into expected value of that, right, because these are not correlated, right? We just talked about something somewhere actually. Okay. Well, maybe somewhere is there. Okay, so, right. Okay, so if you see this expected value of these two, okay, so these are uncorrelated. So, then expected value I can talk about that multiplication of these two. Then I can use this expected value is a linear operator. So, I can take it inside, okay, then mu of x is, I mean expected value of x of t is mu of x, and expected value of mu of x is a number, constant number. So, any constant number and the average or expected value of that is the same constant number. So, I put it that way. Then expected value of that is again by definition mu of y minus mu of y. Okay. So, it turns out to be 0 basically. Okay. And this property will be, again we will use it actually. And there is another definition called orthogonality, and random variables x and y are said to be orthogonal if this r x y of tau turns out to be 0 basically. Okay. If I multiply these two, turns out to be 0, then these signals are called orthogonal actually. All these are in the form of scalars. Then what happens in form of vectors actually. Okay. So, when you have a vector v which has n components, okay, but each of the component are something like stochastic processes actually, scalar components, stochastic processes, then what actually? Then the mean value by definition is nothing but the mean values of everything. These are bunch of definitions actually. Autocorrelation matrix, okay, now it is V transpose, okay, and these are something like outer products actually, remember that. Okay, V is, let us say you have n by 1 matrix, okay, but so this is n by 1, then V transpose, okay, this is n by 1, okay, and so obviously V transpose will be 1 by n. So, the total thing will be n by n, that means it is actually a matrix. Okay. Similarly, autocovariance matrix can be defined something like this. Again, these are typically outer products all the time. Okay, not inner products actually. But also remember, if you have some outer product, well, if you have some V, let me see that. Okay, if you have some outer product, something like V transpose, and if you really want to get inner product V transpose V, then it turns out that is nothing but trace of this actually. So, when you do outer product, it contains inner product information as well. Just take the diagonal elements and sum it up, that will turn out to be the inner product actually. So, the covariance autocorrelation matrix, autocovariance matrix now, and similarly the variance matrix, something like this, and these are something we will call about covariance matrix actually in Kalman filtering. Okay. So, we talk about signal minus the average value, that is the deviation from the mean value, and then operate it again with respect to itself in the sense of an outer product actually, then we will get that. Alright, so this is some sort of a little bit overview of probability theory and stochastic processes and some definitions associated with that and all that. So, before stopping this lecture, again whatever we discussed in the last lecture, let us revisit a little bit. What you are interested in this particular lecture series is gearing up towards this Kalman filter in general. Okay, and then looking back, what we discussed last lecture, we discussed something like continuous time Kalman filter followed by EKF. Okay. So, EKF let us not recapitulate, but let us see how systematically the Kalman filter in the linear domain can be derived and all that. That we will do in the next class, but as a summary sort of thing, this is what it is. The Kalman filter, what we require, the information, and what is the task. So, information required is something like a system model. We need a linear model per se. Okay, if it is not linear, it needs to be linearized first, and then we need some measurements and the statistical behaviors. Okay, and we also need statistical models characterizing the process and measurement noise. And typically, we will assume that they are zero mean uncorrelated white noise. And now it should mean, what do you mean by zero mean, what do you mean by uncorrelated signal, and what do you mean by white noise. It should all make sense now basically. Then also we will need initial condition information for the states actually. So, what is the task? Task is to estimate or filter the state by processing the measurement data and using the system model actually. Okay. So, how do you do that? Very quickly, let us see that. You have x dot equal to x plus v plus gw now, okay, where w is something like a process noise, which is white. Okay, for example, wind gust, unmodeled high frequency dynamics and things like that, and you have this measurement y, which is nothing but cx plus v. Okay, and this v is a measurement noise basically. Okay. You have process noise and you have measurement noise. So, assumption is these noises are zero mean white noise. Now, again it should make sense now what is white noise and all that. Okay. Autocorrelation function turns out to be direct delta function actually. And x of 0 is unknown, initial condition is typically not known really, but it is characterized by something like a mean value and its covariance actually. Okay, how much it is distributed away from the mean value. And W of t, V of t, as we told, it are zero mean white noise, and zero mean means first mu's are 0. Okay, and the kind of covariance is nothing but for W it is Q and for V it is R actually. Okay. Alright, so Kalman filter talks about something like this. You have got a estimator or something like a observer dynamics actually, and it is very close to what we know, the system dynamics here, x plus v plus zw. Obviously, these quantities zw and v cannot be processed, okay, because they are noisy quantities and things like that. They are directly used for some processing only in the particle filtering by the way. Everywhere else these are concepts, they are not used in computation per se. Okay. So, anyway, so coming back, this is what it is. This is estimator dynamics really. So, it got x hat plus vu plus k times y minus y hat, where y hat is nothing but expected value of cx plus v. Okay, that's nothing but y basically. I mean this by definition, okay, y hat is expected value of this. Okay. So, then expected value is a linear operator again. So, we can expand this, okay, and then expected value of E is 0 because it is a zero mean noise, and C can come out and it turns out to be something like this actually. So, y hat is nothing but C x hat. Okay, so that is something like a expected output sort of thing. I mean, this is true output and this is expected output basically. So, there is a difference between them, and that is how it is this observer dynamics or estimator dynamics is operates basically. So, Kalman filter also defines something like covariance matrix, and covariance matrix turns out to be by definition is expected value of x tilde times x tilde transpose, where x tilde is x of t minus x hat of t. Okay, this is, remember, this is two true states and this is estimated state. The difference between that is x tilde basically. Okay. So, P of t is a measure of uncertainty in the estimate. That is why we are more interested in P also basically. We estimate something, but we also want to know a measure of uncertainty in that particular estimate. That is why P of t is important actually. And if the observer dynamics is asymptotically stable, okay, it turns out to be like that, and W of t, V of t are stationary processes, obviously the error will eventually reach a steady state value. Okay. And the idea here is you need to design this KE. Remember, this still is not sure what is KE. We need to still design that. So, the gain KE is chosen so that it minimizes steady state error covariance matrix. Okay. And then optimal gain will be something like a constant matrix. We will see that in the next class. We will derive all that actually. So, in implementation sense, we have got some initial condition, expected initial condition rather. Starting from there, we can compute the Kalman gain, okay, where this P is nothing but positive definite matrix, but it is also this filter Riccati matrix solution sort of thing. So, the Riccati matrix, filter Riccati matrix is something like this. It needs to be solved for P, and once you get for P, this K is ready actually. Okay. Finally, if K is ready, then estimator or filter dynamics is done that way. So, starting with this initial condition, you can propagate it based on the actual measurements actually. Okay. That is it. So, thanks for attention, and then we will continue the derivation in the next class actually. Thank you. Bye.